Alright guys, we're going to talk about empirical formulas, molecular formulas, and combustion analysis today. So I have some processes that are kind of good methods that you should follow. It's nice to have a definite way to approach these types of problems. And I have a lot of examples. So if you feel like you get the hang of it, you don't have to watch all the examples, but I really do recommend you kind of look at the process because this is how I will always do it, and I should expect you should do it the same way. Alright, so when we're talking about EFs, or empirical formulas, those are going to be the simplest ratio. Molecular formulas are going to be ones that could be reduced, but we don't reduce them because they're representing some molecule that has a specific number of atoms in it, of each type of element. So if I give you an empirical formula, and I give you percents in the problem, so like 29% X and 39% Z and on, what I want you to do is based off a 100-gram sample. So if I give you 29% of something, then you're going to call that 29 grams. If I give you 39% of something, you're going to call that 39 grams. And after you get to grams, usually we never use grams when we're getting to formulas because formulas are mole ratios. So I want you then to take the grams and go to moles of each of the element, whatever we're talking about here. There could be 3, 4, 5, doesn't matter. And then, just as an empirical formula, you want to reduce down to the lowest value. So what you do is you divide each value that you have by the smallest number of moles. So maybe you got 0.2 moles of oxygen, 0.4 moles of hydrogen. Well, then 0.2 would be your smallest. You divide all your moles by the smallest value. If by chance you get a number that's not a whole number, not an integer, maybe it's a 0.5 number, then you're going to multiply everything by 2. This is just kind of a cheat sheet here. You need to know these. If you have a 0.33 number, you're going to multiply it by 3. If you have a 0.25 number, you're going to multiply by 4. Those are the easier ones. The 0.67 and 0.75 we don't see too often, but this is how you multiply in order to get it a whole integer. Now that's if you have percents given to you in the problem. If I give you grams, you're already done. You just need to take your grams and go to moles, or sometimes I give you moles, and that part, that's the easiest part because you automatically have your moles. You just need to divide by the smallest number. And this little note here is important just to tell you why we do this, because empirical formulas are ratios of atoms or moles, not masses. So that's what we have to convert to moles. Alright, this example, a sample of unknown compound with a mass of 2.571 grams was analyzed and found to contain 1.102 grams of carbon and 1.469 grams of oxygen. And this is not a percent problem. You're actually going to go straight from grams to moles. So I'm going to start off with this was the unknown compound. We know that it's going to be containing 1.102 grams of carbon. I'm going to go ahead and take this to moles of carbon. So 1 mole of carbon weighs 12.01 grams of carbon. And once you do this, this is 0.09175 moles, and I'm extending my decimal out a little bit because I want to make sure I keep all my sig figs, moles of carbon. And the other value given to me is 1.469 grams of oxygen. This is just elemental oxygen. 1 mole of oxygen weighs 16.00 grams of oxygen. That number is going to be 0.09181 moles. You can do that calculation yourself as well. Now that we have moles, you need to choose between these two, which is the smallest number of moles. That will be the carbon one. So divided by 0.09175 divided by 0.09175. Those are about the same. So we know definitely this is 1. We know this is approximately 1. So when I round, it's going to be 1. And this is now going to tell you the ratio of 1 carbon to 1 oxygen. You can put 1 and 1 there, but that looks silly, so I just like to write it like this. And this is carbon monoxide, so that's a pretty easy one. And most of the time when you have an empirical formula, you should be able to recognize the simple ones, like you should know this is carbon monoxide. Okay, so white powder used in paints, enamels, and ceramics has the following composition. And it gives you all in percent. So you have barium, carbon, oxygen. So this is going to be a 3-element kind of compound. So we actually need to go ahead and take all these percents and turn them into grams. So we have 69.58 grams of barium. My first step is to take my grams and go to moles. And I'm assuming a 100-gram sample. So Whenever I take all of these, it will add up to 100 because all percents will add up to 100. So if I have 1 mole of barium, I look at the periodic table and I see its molar mass is 137.33 grams of barium. Calculating the moles there is 0.5067 moles of barium. My next one is carbon, so I have 6.090 grams of carbon. Take that to moles. 1 mole of carbon. Periodic table weighs 12.01 grams of carbon. And that is 0.5070 moles of carbon. Lastly, we have oxygen, which is 24.32 grams of oxygen. 1 mole of oxygen, this is all stoichiometry, is 16.00 grams of oxygen. This is going to give me 1.52 moles of oxygen. Okay, now that everything is in moles, we need to look and see which one is our smallest number of moles. That's barium here. If we divide all of these numbers by 0.5067, divide all of the rest of these by 5067, divide by 0.5067, and I could put moles on all these, but what we're determining here is just the ratio. So this number divided by the same number is 1. This is, you can look and see they're very similar, so that's going to round to 1. And then we have 1.52 divided by 0.5. That's going to be 3. So our ratio is going to indicate our subscripts, which would be barium will be a 1, carbon will be a 1, and then oxygen will be a 3. And if you look at that, you're seeing barium carbonate. And you know that's correct because you know that barium is a 2+ charge. You know that carbonate is a 2- charge. When you crisscross, you get barium carbonate simplified to this formula. All right, and how do you know what order to put it in? If you have a metal, put the metal first, and this you may have written O3C, but then if you look at it hard enough, you might recognize that it's going to be an ionic compound, so it needs to have a polyatomic ion, and the only one you know is carbonate there. So if I ask you about a molecular formula, usually what I will have to do is give you a molecular weight. So that's going to be a larger number, or I might say the molecular mass of some compound is 284 grams per mole. So what you have to do first is to get the EF, or the empirical formula. Then you're going to look at the empirical formula, get the molar mass of that, compare it to the molecular weight, or the molecular formula, and see how many times you can fit that EF mass into the molecular weight of the molecular formula. So what you will do is you're going to take the molecular mass divided by the EF mass to get you a number called N. And then what you do is you take the EF, the empirical formula, and then you multiply each subscript by N to give you the molecular formula. It's just a multiple of it. So for example, given a molecular mass of 250 grams per mole, and you already have your EF indicated here, and the molar mass of that you've already decided is 125 grams per mole, what you do is you say 250 grams per mole divided by 125 grams per mole. That's going to be 2. So 2 is kind of the N number, meaning you can fit 2 EFs into an MF. So if your formula, I'm just going to call it X, Y, you're going to take the 2 and multiply both of these 1 subscripts by it to give you X2, Y2. And this right here is the molecular formula. All right, let's do an example. An oxide of phosphorus, so I'm not telling you the formula, but I'm telling you what's in it, is 43.7% phosphorus and has a molecular weight of 284 grams per mole. Determine the molecular formula of this compound. All right, so this is really slim information here. We do know that when we have a percent, we're going to assume a 100-gram sample, and we know that the other bit here is oxide, which is oxygen. So we know that of phosphorus, we have 43.7 grams of phosphorus, taking that percent and going to grams, and take 1 mole of phosphorus weighing 30.97 grams. When I take that to moles, I get 1.411 moles of phosphorus. All right, so for oxygen, we need to actually figure out how much oxygen we have. If we know that we have 43.7 of phosphorus. Take 100 minus 43.7 to give you 56.3. So that's the percent oxygen, meaning that's what we assume in grams. 56.3 grams of oxygen. 1 mole of that is 16.00 grams. And that number is 3.52 moles of oxygen. So in both of these, your smaller number is the phosphorus one, so divided by 1.411, divided by 1.411 on both. This is 1, and this number is 2.5. Okay, I can't have a non-integer, so I have to multiply both of these ratio numbers by some number to make whole numbers. If I have a 0.5 value, I multiply both of these by 2. So now I have phosphorus is 2, oxygen is 5. So these new numbers here, this one and this one, are my subscript numbers. So I get phosphorus 2, oxygen 5. Okay, let's look at the mass of this and determine if this is our molecular formula or not. When you add up your mass, phosphorus each weighing 30.97 and oxygen each weighing 16, you get 141.94 grams per mole. Okay, so apparently this is not our molecular formula because up here it tells us that 284 grams per mole is our molecular mass. Meaning all we need to do now is take the molecular mass divided by the EF mass. So that's 284 grams per mole divided by 141.94 grams per mole. You can probably look at that and see it's about 2. So the N number is 2, and then we need to raise all the subscripts to that 2. So P2O5, multiply the subscripts by 2, would be P4O10. And this is tetraphosphorus decoxide. Alright, so for combustion analysis, you have to know that in combustion we always have a hydrocarbon reacting with oxygen. And if you get into your independent study with organic chemistry, you'll get a lot more information about hydrocarbons. When we react with oxygen, we always make carbon dioxide and water. Doesn't matter if it's a hydrocarbon with just carbon and hydrogen or a hydrocarbon with carbon, hydrogen, and oxygen. Okay? But what we do need to see is that the only source for this first example of carbon is from the hydrocarbon. And that's going to be transferred, rearranged to form carbon dioxide. Hydrogen is going to be changing form into water. So if I give you information about the products here, if I give you a certain number for carbon dioxide and a certain number for water, you can work backwards to figure out how much carbon and hydrogen I had initially. This oxygen is being, split up into 2 different products. Same thing here in terms of the carbon and the hydrogen, but oxygen now could possibly come from either of these sources in our products here. This one's harder. It's not really harder, it just takes a couple more steps. This one's the easier of them, so I'm going to do one of each of these examples. And I call this combustion analysis because what we are actually analyzing is the combustion product. So we're going to look at the relative amounts of carbon dioxide in water collected. And this is the apparatus that collects it. We have a furnace where we actually combust. We have a collection tube that's going to be absorbing the water, and a collection tube that's absorbing the carbon dioxide. And the other substances not absorbed would be excess oxygen usually, and that's going to be just because we have a lot of oxygen present in combustion reactions. This is the apparatus for it. Alright, so example 1, a compound contains only carbon and hydrogen. That's easy, so we know we have CX, H, Y, so that's going to be our kind of formula. A 1.45 gram sample is burned and produces 2.25 grams of water, 4.4 grams of carbon dioxide. Determine the empirical formula. Okay, so we need to kind of set up our reaction here. We know that CXHY plus oxygen yields carbon dioxide and water. Sometimes I like to do this because it kind of keeps my facts straight. A 1.45 gram sample. So 1.45 grams of the sample is burned. We don't know how much oxygen we had. And it produces 2.25 grams of water and 4.40 grams of oxygen. Okay, so the way that you should start this is I usually start with carbon dioxide, just because I like to. I'm going to start with 4.4 grams of CO2. What I want to do is I want to figure out how much carbon is present in moles, so then I can then convert and see how many moles of carbon I initially had. So I need to go ahead and go to moles of carbon dioxide. Carbon dioxide weighs 44.0 grams. And then I actually don't want to stop at moles of carbon dioxide. I want to go all the way to moles of carbon. So here's my mole ratio. 1 mole of CO2 has 1 mole of carbon in it because it's got 1 carbon in it. Okay, so here I get to 0.100 moles of carbon. Okay, leave that there for a second. I'll get back to it. All right, now for the hydrogen, I need to look at the water. So I need to get this water down to moles of H, or hydrogen. So starting with 2.25 grams of water, 1 mole of water is 18.02 grams of water. And now I need to get to actually moles of H. So 1 mole of water has 2 moles of hydrogen in it because of the 2 right here on the subscript. Here, this is going to give me 0.250 moles of hydrogen. All right, so between these two, I need to look now and see who's my smaller. This is kind of just an empirical formula problem. It's just a little bit different on our setup. If I look, I see I have 0.1 moles of carbon. That's a smaller number. So I divide both of these by 0.1. This is going to give me 1. This is going to give me 2.5. Okay. You know that I can't have an integer such as this, so I have to multiply both of these by 2. So that's going to give me carbon is 2, multiply the 2.5 by 2 is going to give me 5, meaning I have C2H5. When I do this, I can, kind of just make sure that this makes sense. You can go back through your math if you're not sure, but this is a good formula. This is actually an ethyl group. It doesn't usually exist by itself, but this is a good example for this. Okay, so this next one is the more complex one because it says you have 5 grams of an oxygen-containing hydrocarbon, meaning we have CXHYOZ. Okay, so we've got 3 elements here. Is combusted to yield 9.57 grams of carbon dioxide and 5.87 grams of water. What is the empirical formula? All right, so here we go again. CXHYOZ plus oxygen yields carbon dioxide and water. I have 5 grams of this compound. I don't know how much oxygen I have yet, but I will. I have 9.57 grams of carbon dioxide and 5.87 grams of water. This right here, I can actually attain. I should know how many grams we have here because of the law of conservation of mass. Okay, the law of conservation of mass is going to tell me that whatever I have on the product side, grams wise, I should have reacting on the reactant side. So when I do the math, I get oxygen is 10.44 grams. We'll use that shortly. All right, so we're going to start off the same way we did. We know that we can get to the carbon component and the hydrogen component using our analysis of the products. So we have 9.57 grams of carbon dioxide times 1 mole of carbon dioxide, which is 44.01, I think, grams is what I said earlier. And I need to go to carbon, so 1 mole of carbon dioxide has 1 mole of carbon in it. And I'm going to stop right here, and I get 218. Let me fix that. Eraser. All right, 0.218 moles of carbon. Okay, that's an important number. And then I'm going to leave a little space right here because I'm going to use this space in just a moment. For the hydrogen, I need to get from water 5.87 grams of water times 1 mole of H2O, weighing 18.02 grams of H2O. And then I have, 1 mole of H2O containing 2 moles of hydrogen. That's a 1 right there. That's a big one. Okay. I'm going to stop here and get that hydrogen. I have 0.652 moles. Okay, so this number is important, so I just like to square them if I need to. Now, for the oxygen, I need to figure out how much oxygen I have here in the initial compound, but I've got oxygen present in carbon dioxide and in water, and I know that I only had, I had an excess, or I had a certain amount of oxygen that was just being reacted with the hydrocarbon. So the way I do this is I analyze how much oxygen came from the carbon dioxide here, how much oxygen came from the water here, and then I'll see how much I have excess left over. So this is the same, but when I get here, I'm not going to multiply, I'm not going to look for carbon, I'm going to look for oxygen. So 1 mole of CO2 has 2 moles of oxygen in it. So I just took 9.57 divided by 44, and then I'm going to multiply by 2 here to give me 0.435 moles of oxygen. Okay, same thing down here for water. Same thing, but here I'm going to say 1 mole of water contains 1 mole of oxygen. So that number is going to give me 0.326 moles of oxygen. Okay, we're going to get back to this number in just a second. Now let's take our 10.44 grams of oxygen that we have figured out due to the law of conservation of mass of O2, and I actually want to bring that to moles. So moles of just O. So I take 1 mole of oxygen, of diatomic oxygen, which weighs 32.0 grams of oxygen, diatomic, and now I'm going to isolate just 1 atom of oxygen. So 1 mole of O2 contains 2 moles of just the element oxygen. Here this gives me 0.6525 moles of oxygen. Okay, so these oxygens, what we need to do now is analyze what oxygen was found in the product. I'm going to minus this excess that was just another reactant. Whatever's left over should be what was found here in the reactant, the hydrocarbon reactant. I'm going to change pink color so we can clarify this. Okay, so here we now need to take the oxygen found in products, which was 0.435 moles from the carbon dioxide, and this is in addition, plus the 0.326 moles of oxygen that we found in the water, and that is equal to 0.761 moles of oxygen found in the products. That's the total oxygen that would be present. If we minus the 0.6525 moles of oxygen from O2, then we're going to get some leftover oxygen, which is 0.1085 moles of oxygen in the hydrocarbon. Okay, so in the products we should have all oxygen from every source of oxygen in the reactants. We minus out the O2 oxygen that we found from the 10.44 grams. We get this leftover oxygen right here. Now, this is the number that we are going to use when we talk about the empirical formula. So now what I'm going to do is I'm going to look at this number, 0.218, the hydrogen, 0.652, and this oxygen number, 0.1085. I'm going to look for the smallest one, which would be the oxygen. I'm going to divide by the smallest number of moles. So I'm changing pen colors again to kind of keep this organized. So here we divide by 0.1085. This number divided by 0.1085. And this number divided by 0.1085. This is going to be 1, obviously, because that's just our moles of oxygen. The top one with carbon is going to be approximately 2. And the hydrogen one is approximately 6. Okay, so if you're looking at your calculations, you're going to be rounding to those integers, meaning our final answer is carbon 2, hydrogen 6, oxygen 1. Okay, this is our final answer. This is the empirical formula of our hydrocarbon. So I told you this one was longer because you really have to organize your thoughts and go through carbon first, then hydrogen, And then if you'd like to, go like I did and go back and do the oxygen for each of the components of the products. And then you look at the oxygen that you had reacting with the hydrocarbon. The difference is going to be the amount of oxygen that was in the hydrocarbon. That difference is the moles that you look at when you're doing your EF, your empirical formula. All right, this was a hard one. If you have any questions, let me know. I'm here all the time, so obviously work at it and then ask me